The spring of 1943. High above the Ruhr Valley, 8 B-17 Flying Fortress from the 91st Bombardment Group leveled off at 30,000 feet. The temperature outside the aluminum skin of the aircraft was minus 50 degrees Fahrenheit. Inside the plexiglass nose compartment, hunched over a cylindrical instrument roughly the size of a large thermos flask, the Bombardier pressed his eye to the eyepiece of the most closely guarded weapon in the American arsenal. Below him, through a thin scatter of high cloud, lay a synthetic oil refinery that the 8th Air Force had been ordered to destroy. The target was a cluster of buildings, storage tanks, and distillation towers spread across several acres of German industrial ground. From 6 miles up, it was a gray smudge against a darker gray grid. The Bombardier made a series of small corrections to 2 knobs on the instrument beneath him. He waited. The airplane flew itself. The bomb bay doors were already open. The instrument, not the pilot, now controlled the aircraft's final approach path. At the computed release point, a small circuit closed inside the device, and a row of 500-pound general-purpose bombs dropped free in a tight pattern. The Bombardier lifted his eye from the eyepiece and watched smoke begin to rise from the target below. What he had just done, from 30,000 feet, with no computer in any electronic sense of the word, no satellite guidance, and no ranging system beyond machine gears and a gyroscope, should not have been possible. Most of the German officers reviewing bomb damage assessments from that period did not believe it was. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. The Norden bombsight was not built for war. Carl Lukas Norden was a Dutch-born mechanical engineer who had emigrated to the United States in 1904 and spent the following 3 decades designing gyroscopic stabilizers for naval gunfire control systems. He began working on the bombsight problem in the early 1920s, initially under contract to the United States Navy, which had a practical need. Its aircraft had to be able to hit ships at sea from altitude, and the available methods were producing results that no operational analysis could defend. Dropping a bomb from a moving aircraft onto a target while compensating for wind speed, aircraft speed, altitude, and the ballistic arc of the falling ordnance was a problem that no mechanical instrument had solved with any dependable accuracy. The Army Air Corps at that time did not believe high-altitude precision bombing was operationally viable. Its doctrine centered on low-altitude attack. Close in, release, pull away. The problem was survivability. Anti-aircraft batteries could track a low-flying aircraft with relative ease, and fighter aircraft could engage at effectively below 10,000 feet. The argument for high-altitude precision bombing was military. If it worked, bombers could reach their targets above the effective ceiling of most ground-based fire and beyond the performance envelope of most interceptors. The problem was accuracy, and accuracy was what Norden spent 20 years trying to provide. His solution was a gyroscopically stabilized analog computing device that held 4 variables in continuous mechanical balance: the aircraft's true airspeed, its altitude above the target, the wind's drift effect on the bomb during its fall, and the ballistic coefficient of the specific bomb type on the racks. The Bombardier used 2 control knobs to track the target through the eyepiece, keeping a set of crosshairs centered on the aim point as the aircraft flew its approach. The sight's internal gear train translated those tracking corrections into a running solution for the precise release point. When a solution was current, the mechanism triggered bomb release automatically through an electrical connection to the shackles in the bomb bay. The device also connected to the aircraft's autopilot, designated the C-1, allowing the bombsight to steer the aircraft during the final minutes of the bomb run by making small adjustments to heading. The pilot handed over control at the initial point, the last navigation fixed before the target, and the aircraft flew the final approach under the sight's direction. Norden spent more than a decade refining the mechanism between his first Navy contracts and the version the Army Air Corps accepted in the late 1930s. The production model, the Mark 15, weighed approximately 50 pounds, occupied roughly the space of a large typewriter, and contained a gyroscope, a rate of turn indicator, and a series of interconnected gears and levers machined to tolerances measured in thousandths of an inch. The Army Air Corps classified it at the highest level applicable to a piece of ground equipment. The technical manual was kept in a locked safe aboard each aircraft. Bombardiers swore an oath to destroy the device rather than allow it to fall into enemy hands. Each site carried a serial number and was tracked individually in the Army Air Corps inventory system. When AB-17 went down over Europe, the loss of a Norden aboard, it was recorded separately from the loss of the aircraft itself. The performance claims made for the Norden in official Army Air Corps documents were extraordinary. Tests conducted at the proving ground at Muroc in California showed that under controlled conditions, at altitudes between 15 and 20,000 feet, trained bombardiers using the Mark 15 could place 50% of their bombs within a circle 100 feet in diameter. 100 feet from 30,000 feet of altitude. The Air Warplans Division built an entire targeting doctrine around that figure. If the Bombsight could deliver in combat what it delivered at Muroc, then American bombers could do something that no bomber force in the world had managed: destroy specific industrial installations from altitude without leveling everything around them. The doctrine was called precision daylight strategic bombing, and its entire logic rested on the Norden delivering in combat what it had demonstrated in California. AWPD-1, the strategic bombing plan drafted in August 1941, identified specific industrial systems whose destruction would cripple German war production, electric power generation, transportation infrastructure, oil production and refining, and aircraft manufacturing. The theory was that destroying a small number of precisely identified nodes in each system would produce cascading failures through the German war economy. A rail junction destroyed meant supplies delayed. A ball bearing plant damaged meant a shortfall in the components that went into every aircraft engine, every tank wheel, every artillery piece the Reich produced. The Norden was the instrument that made the theory operationally viable. Without a bomb sight capable of hitting individual factory buildings from above effective anti-aircraft range, the targeting logic collapsed entirely. The British had already concluded, from their own experience over Germany, that such precision was beyond reach in combat. Their analysis was grounded in the Butt Report of August 1941, a study commissioned by Churchill's chief scientific advisor Frederick Lindemann and conducted by a civil servant named David Ben Susan Butt, who examined photographs taken on Royal Air Force bombing missions and found that only one aircraft in four that claimed to have attacked its target had placed bombs within 5 miles of the designated aim point. 5 miles. Over the Ruhr, where industrial haze and searchlight glare were constant, the figure was 1 in 10. RAF Bomber Command's response was to shift to area bombing at night, targeting city centers and industrial districts broadly enough that even large errors still produced useful damage. The American planners believed the Norden changed the arithmetic entirely. If the Muroc tests accurately predicted combat performance, American bombers could do what British bombers could not. The Germans and the Japanese had each learned of the Norden's existence through intelligence before the war began. Germany had received detailed technical drawings of an early version of the sight in 1937, delivered by an agent named Hermann Lang, who worked at the Norden manufacturing plant on Lafayette Street in Manhattan. Lang passed the material to the Abwehr, and German engineers examined what they received. Their conclusion was that building the device to the tolerances the drawing specified would push German precision manufacturing to its limits. They were correct. No German equivalent ever matched the Mark XV's measured performance, and the German effort to develop a comparable high-altitude bomb sight was eventually deprioritized in favor of the night fighting and ground attack capabilities German doctrine emphasized. The Japanese reached similar conclusions independently. What neither power could replicate, they attempted to neutralize through tactics: dispersal of industrial targets, underground production facilities, and fighter interception aimed at disrupting American formations before they reached the bomb release point. The training a bombardier received before he was assigned to a combat group was structured entirely around the Norden's specific requirements. Bombardier school ran approximately 20 weeks, split between ground instruction and practice flights over bombing ranges. The ground instruction covered the site's mechanical principles in detail, the calculations the gear train was performing in real time, the relationship between altitude and bomb trajectory, and the effect of wind at different altitudes on a falling 500-pound object. Instructors stressed that the bombardier was not aiming the bomb. He was providing the instrument with accurate input data and then holding the crosshairs steady while the mechanism computed the release point. His job was to feed the sight correctly and to remain steady while it worked. Practice missions over bombing ranges in Texas and New Mexico allowed cadets to develop the tracking discipline the site required. A good tracking run, where the bombardier held the crosshairs without overcorrecting, produced a tight bomb plot near the target center. A poor one, where corrections came too fast or too hard, scattered the bombs across a wide pattern. The scores were recorded and used to determine whether a man was suited to the Norden or should be reassigned. The training produced real capability. Cadets who completed the course and demonstrated consistent accuracy on the practice ranges were capable of putting bombs on a target from altitude in the conditions the training ranges provided. What the schools could not supply was what happened when the conditions were not controlled, when the target was obscured by cloud, when the aircraft was being thrown around by flak bursts, when a man at the eyepiece had been awake for 20 hours and his hands were shaking from cold that no California practice mission had prepared him for. The men who flew the bomb runs also had to contend with a problem the training syllabus addressed, but could not fully replicate: the compressed timeline of the final approach. From the initial point to the bomb release point, AB-17 at 250 miles per hour covered the distance in minutes. During those minutes, the formation was committed to a straight and level course. No evasive action, no deviation from the assigned heading. The bombardier had to hold the aircraft on the autopilot through the site, make his final tracking corrections, and maintain the solution while German anti-aircraft guns tracked the formation and adjusted their fire. Every gun crew in the target area knew that an aircraft flying straight and level was on its bomb run. The flak was heaviest and most accurate in those final minutes. The psychological demand of holding steady while shells burst around the aircraft, fragments ringing off the fuselage, other aircraft going down in the formation, was a thing the Muroc tests had not measured and could not have measured. The site could hold the solution mechanically. It depended on the man behind the eyepiece to hold it as well. The formations themselves added a layer of complexity to the Norden's performance that the individual bombardier could not fully control. The site's precision depended on a stable platform. AB-17 flying straight and level in clear air provided a reasonable approximation of that stability. AB-17 being buffeted by the slipstream of dozens of aircraft flying in close formation, its wings flexing through prop wash, its altitude varying slightly as the pilot held position against the aircraft above and ahead, was a less cooperative partner for an instrument measuring drift in thousandths of a degree. The problem was most acute for the aircraft flying trail positions in the formation, where accumulated turbulence from the aircraft ahead made a stable bomb run harder to maintain. Wing bombardiers in the trail positions knew their accuracy was likely to be worse than the lead aircraft. The mission reports reflect this, showing tighter bomb plots from the lead and deputy lead aircraft and progressively wider dispersal toward the trailing positions. The 8th Air Force's solution was to concentrate scoring criteria on the lead bombardier's performance, accepting that the rest of the formation would bomb on his signal regardless of their individual tracking solutions. The Norden's capability was therefore being expressed through one bombardier per formation, and the rest were following his release cue. When the lead bombardier's solution was good, the formation placed bombs accurately. When it was not, the whole formation missed together. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. What the Norden actually achieved in combat, measured against what the proving ground tests had promised, is a more complicated record than either the Air Corps' wartime claims or its sharpest critics would later acknowledge. The controlled tests at Muroc had been conducted in clear skies. At altitudes bombardiers had trained it repeatedly, against fixed targets with known coordinates, without enemy fighters pressing the formation during the approach, and without anti-aircraft shells bursting around the aircraft during the final minutes of the bomb run. No test had required the bombardier to work the site's knobs with hands numbed by cold reaching 40 below zero inside the plexiglass nose. No test had placed the aircraft 3 minutes from the target, while Focke-Wulf 190s attacked from 12 o'clock level. After-action reports from the 306th, 303rd, and 91st Bombardment Groups, available at the Air Force Historical Research Agency archives at Maxwell Air Force Base in Alabama, show that circular error probable figures from actual missions over German targets ranged from several hundred feet on favorable days to well over a mile when conditions were poor. The phrase "on favorable days" carries considerable weight. because favorable conditions over the Ruhr were genuinely rare. Cloud cover blanketed Germany's industrial heartland more than 200 days per year. Bomber formations that arrived at the target and found it obscured under cloud resorted to bombing by radar, using a system called H2X that could detect the general outline of an urban area but could not resolve individual buildings at any useful accuracy. The records show this happening on a substantial fraction of missions across 1943 and 1944. The Bombardier aboard the lead aircraft tracked a radar return rather than a visual aim point, and the aircraft behind dropped on the leader's signal, spreading the bomb pattern, but removing the precision the Norden had been designed to provide. Major General Haywood Hansel, who commanded the XXI Bomber Command in the Pacific and was among the most committed advocates of precision daylight bombing in the senior Air Force's leadership, wrote after the war that the doctrine had required conditions that combat could only rarely supply. The operational environment, the weather over Germany, the quality of German air defenses, and the demands placed on aircrews flying at extreme altitude under sustained fire had all worked against the precision the Norden had demonstrated in California. Hansel did not conclude the site had failed. His argument was more specific. On missions where conditions were adequate, where the target was visible and identifiable, where the formation held its spacing and the lead bombardier had the time and platform stability to work the site's solution through to completion, the Norden delivered results that no other bombing instrument in any other air force could approach. A mission against the Erkner ball-bearing plant southeast of Berlin in March 1944 placed a high proportion of hits inside the plant boundaries from above 25,000 feet. The plant's production capacity was reduced for several months by a single raid. The second Schweinfurt mission in October 1943, which cost 60 aircraft out of 291 dispatched, placed enough bombs on the ball-bearing complex to suppress production materially for weeks afterward. The loss rate on that mission, more than 1 in 5 aircraft that crossed the German border, forced the 8th Air Force to halt deep penetration raids for several months, while long-range escort fighters were made available in adequate numbers. Those fighters, the P-51 Mustangs that began arriving in sufficient quantities in early 1944, changed the operational calculation again. With escort cover reaching the target, the formations could hold their spacing long enough for the bomb run to work. Albert Speer, Germany's armaments minister, wrote after the war that sustained American pressure on the ball-bearing plants could have created critical shortages within months. He described the American halt of deep penetration raids after the second Schweinfurt mission as a strategic error that extended the war. Speer's account is self-interested in several respects, and military historians have examined its claims at length. What the bomb damage photography confirms is that on the missions where the Norden operated in the conditions it was designed for, the bombs reached the right buildings. The oil campaign that followed in 1944 is the clearest measure of what the Bombsight, adequate targeting intelligence, and sufficient operational resources could produce when applied against the right systems. The United States Strategic Bombing Survey, compiled from analysis of German production records after Germany's surrender, concluded that attacks on synthetic fuel plants beginning with the Luna raid on May 12, 1944, produced results that were decisive to the air war over Germany. German aviation fuel production fell sharply after sustained attacks on the Luna, Politz, Brux, and other synthetic oil facilities through the summer and autumn of 1944. By that autumn, the Luftwaffe was curtailing pilot training hours because fuel was genuinely scarce. German fighter pilots were going into combat with fewer total flying hours than their opponents, and the difference was measurable in their performance against escort formations. The survey's language on the oil campaign was direct. It shortened the war. The Norden did not end the war alone, and the doctrine built around it had overpromised in ways that cost thousands of airmen their lives on missions that fell short of what planners had projected. Those two findings sit in the same archive, and neither cancels the other. Sergeant Chester Phillips, a bombardier with the 388th Bombardment Group, who completed his combat tour in November 1944, described working the Mark 15 in a debriefing transcript held in the Air Force Historical Research Agency archives. The language in the transcript is plain and technical. Phillips described the final minutes of a bomb run on a rail junction at Ham as requiring patient, close adjustment work, the deliberate small movements of a man doing fine mechanical work rather than the violent action the word combat usually implies. The target crept into his crosshairs. He made corrections. He held it. The bombs went. The post-mission photography showed a direct hit on the main switching yard. His crew had dropped from 22,000 feet. The mission had encountered heavy anti-aircraft fire. 2 aircraft in the formation had gone down before the release point. Phillips's account of working the site under those conditions describes something harder and less certain than any test flight, performed by a young man under pressure that no proving ground had replicated, with a piece of equipment that had been designed in a factory loft in Manhattan to solve a problem most people had assumed was insoluble from high altitude. His debriefing does not record what he felt when the post-mission photography came back with the switching yard in the target area, covered in bomb craters. The archive does not carry that. What it carries is the data, the altitude, the heading, the bomb type, the impact coordinates. The rest is the record silence. The mechanics of how the site solved its problem are worth describing precisely, because the mechanism's precision is what separated it from every alternative the era produced. The Bombardier's task during a bomb run began several minutes before the release point. He established the aircraft's altitude above the target by cross-referencing the altimeter reading against known ground elevation data from the mission briefing materials. He dialed that figure into the site. He entered the aircraft's true airspeed as corrected for altitude. He set the ballistic index for the specific bomb type on the racks below him, encoding the drag coefficient and drop curve the mechanism would use in its calculation. Wind drift he established by observing the target's apparent movement across the crosshairs during the approach, making small corrections to the tracking until the crosshairs moved straight toward the aim point without lateral drift. With those inputs set, the gear train ran its solution in continuous real time. The gyroscope held the line of sight stable against the aircraft's roll and pitch. When the tracking rate the Bombardier maintained through the eyepiece matched the computed rate the mechanism expected, the bombing solution was current. The Bombardier held that state, made small corrections as the aircraft moved, and waited for the circuit to close. At the computed release point, the mechanism triggered the shackles, and the bombs fell in whatever pattern the bay had been loaded for. The Bombardier had no further role. The site had made the final decision. The Norden Secrecy outlasted the conflict by years. Technical manuals and production specifications remained classified well into the 1950s. Carl Norden himself received little public recognition during the war because the Army Air Forces could not publicize the instrument's details without compromising its classification. He continued working from his New York office through the conflict, consulting with engineers on production tolerances and refinements to the mechanism. After Germany's surrender, teams from Army Air Forces Technical Intelligence moved into the Reich specifically to recover Norden sites from crashed American aircraft on German soil before Soviet forces could reach them. The serial number accounting that had begun before the war ran through the end of it. The post-war audit showed that across the entire European air campaign, no complete functioning Norden Mark 15 had been recovered intact by German forces from a downed aircraft. The oaths the Bombardiers had sworn had held. Norden declined a post-war Air Force recognition invitation. He died in Zurich in 1965, at the age of 83, having spent more than 2 decades designing an instrument that guided more bomb loads onto more targets than any other aiming device in the history of aerial warfare, and having spent those same years classified out of any public account of what his machine had done. The preserved Mark 15 bomb sites that survive today are held by several institutions. The National Air and Space Museum in Washington has examples in its collection, including one removed from AB-29 that flew missions over Japan. The Air Force Museum at Wright-Patterson Air Force Base in Ohio displays one alongside the nose section of a B-17 fitted as it would have been for an operational mission over Germany. The mechanism looks, to a modern eye, like something from a different world. Gears and gyroscopes, ground glass and calibrated knobs, a 4-variable physics problem worked out in machine metal with no electronics of any kind. It weighs 50 pounds. Its memory is the precision of its tolerances and the steadiness of the hand that worked its knobs at 30,000 feet. The documents surrounding in the archives, the mission reports, the crew debriefings, the bomb damage photographs, the post-war survey findings, the classified manuals eventually open to researchers, are the record of what it actually did across 3 years of combat over Europe and the Pacific. That record is neither the surgical precision the pre-war tests promised, nor the failure its critics argued. It is something more specific, a mechanical instrument of genuine capability, used by young men under conditions the designers had not anticipated, to do something that no other air force in the world consistently attempted. The bombs that reached the Erkner plant, the Luna complex, the Schweinfurt factories reached them because Carl Norden spent 20 years machining the gears to the right tolerances, and because a bombardier held his crosshairs steady and trusted the mechanism to close the circuit at the computed moment. That is what the record contains. The post-war assessment of a Norden by the United States Air Force was not triumphant. The Strategic Bombing Survey's conclusions, taken together with the operational data from the European and Pacific campaigns, forced a reconsideration of what high-altitude precision bombing had actually delivered and at what cost. The survey identified the oil campaign and the transportation campaign of 1945 as the most effective applications of the doctrine. It was more measured about the earlier missions, acknowledging that the combination of weather, German defensive measures, and the technical limitations of extreme altitude bombing had produced results well short of what AWPD-1 had projected. The survey did not recommend abandoning strategic bombing. It recommended refining the targeting theory, improving weather forecasting, and developing bombing aids that could function under overcast conditions. Those recommendations shaped American air power doctrine through the Korean War and into the early jet age. The Air Force retired the Norden from frontline service in the early 1950s as aircraft speeds and altitudes increased beyond the ranges the site's original design had been calibrated for. Guided munitions and more sophisticated bombing computers began replacing mechanical bomb sights in high-performance aircraft. By the time the B-47 Stratojet entered service as the primary strategic bomber, the era of the optical mechanical bomb sight was ending. The problems Norden had spent 20 years solving in machine metal and ground glass were being handed over to electronics. The bombardiers who trained on the Mark 15 and flew their combat tours are largely gone. What they left behind is the documentary record, the after-action reports, the debriefing transcripts, the bomb damage photography, and the unit histories held at Maxwell Air Force Base in Alabama, at the National Archives in College Park, Maryland, and at smaller repositories across the country. Those documents are the evidence from which any honest account of the Norden must be constructed. Thank you for staying with us until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.